Good afternoon, everybody. We're almost there. The conference is almost over. So we're going to make this as exciting as possible. We have Science Matters, the effect of cushion setup on tissue deformation and posture. So who are we? I'm Bart. I'm from Belgium. That's why I speak so funny. I try to speak as good as I can, but it just doesn't get any better than this. So I apologize for that. Yeah. So if you don't understand me, it's my fault, not your fault. And I want to disclose that I have my own private practice with my wife. And I also own Superseding, which is basically my consulting work. And I do seminars, training sessions for clinicians worldwide, for companies if they hire me, and R&D activities and regulatory work, I do that too. And Alexander Siefert is from Germany. You want to introduce yourself, or should I?
No, just go ahead.
He's my German friend, and he's the owner of Virtual Human, GmbH, which is his own company, and he provides engineering services, and I'm very excited about what he's done, and we just finished the presentation, so it's very excited, just in time, about 10 minutes ago, but yeah. I think it will be good. Yeah. So, and we teamed up because I have a lot of clinical questions, and there's not always research out there, and I think I know Alexander a long time, so we partnered up and we wanted to see if we could work together and provide more guidance to our clinical practice. So that's why we are a team. So, and today we will do some of the work. And what we're going to do today is a little bit of, we will see if we can make our clinical decision making better and more efficient. And we're going to explain to you how finite element analysis, basically Alexander's work, can help us or can assist us with making clinical decisions. What is human body modeling? So we're going to cover that. Alexander is going to show his work and how it works. And then ask a couple of specific questions. I had a lot of questions on my list. Unfortunately, the list was too long, so we had to pick, and it was last summer when we came, when we sat together. We said, well, what can we analyze and what can we provide answers on? And we have a couple of things that really are interesting. We have the squeeze effect. So basically, what is the effect of your seat width on tissue and on posture? We're also going to examine what the influence is of knee angle adjustments when you have, for instance, short hamstrings, and what's the effect on tissue. And we're also going to examine what the effect is of backrest tilt, back support tilt. And we're going to also see what the conclusions are after the session, right? So the way I work is probably very similar as to how you work. If I have a very complex problem or if I have a seating issue, whatever that may be, I try to first understand and define exactly what that seating issue is. And then I guess the tough part begins. You have to use your brain. We don't like that, but brains is good. And your brain is basically what is the research, what is your experience, what are the courses, what did I learn from past experiences, and that probably provides you guidance to what the next step should be, and that's your assessment, because we all know that everybody is different, and we can't put people in a diagnostic category. They all have their individual needs, and everybody is different. So we need to examine specifically things that we need in order to solve the user's needs. And then we have to realize something, we have to build something that's basically, or adjust or make a change to make it work. And then, of course, we have to track, and that's your outcome measures, or see if what you did was the right thing or not, and that's usually a winner. And we all know that we sometimes forget this, so that's why if you take the first letter of every little chapter there, you have Bart, and I'm Bart, right? So So perhaps you remember it now, so I don't know. You're right. So we looked at a couple of very simple parameters, so the first question I had was something that is so normal and that we all basically do on a very regular basis. We select the width of a wheelchair or of a seat cushion, but if you select the width of the seat, it is already important. The wheelchair width is important. And I was looking at, and I talked to a couple of my colleagues. Actually, I've been to several lectures, and some clinicians say, you have to squeeze the wheelchair a bit. It's like you have to make it really fit. And even if you have a lot of adipose tissue, well, you can even squeeze that tissue a little bit because that will provide you more stability. Does that sound familiar? Some people say, look, we're not going to do this. We stay 1 finger thickness away from the most lateral point of your pelvis. So you make the wheelchair a little bit wider, and that corresponds with 2.5 centimeters or roughly 1 inch. And some people say, no, I go in the middle. I make it a little bit bigger. Than the wheelchair user's width, so the distance between the most lateral point of the pelvis. So there's a lot of opinions about this, and we know we make those calls on stability needs, on transfer needs, but also we have to take tissue deformation and pressure ulcers into account. But there's not a lot of research out there. So I looked a little bit to see what was being published. And very recently, there was a study published by Stevens and Bartley. And the idea, it was published in the Journal of Tissue Viability in 2018. And the purpose of that publication was to provide seating guidelines for the Tissue Viability Society. So this will be likely to be adopted by the Tissue Viability Society as a recommended width selection of your wheelchair. And the paper states, so I didn't write it myself, but the paper states that the seat width is important because it can affect the posture and pressure areas. Nothing new there. If the seat is too narrow, it can lead to pressure damage at the hips, buttocks, and the back of the knees. If the seat is too wide, the person may feel unsupported, which could result in posture and pressure problems with the hip and the spine. It also may be difficult to fix equipment to the seating system, such as lap belts, hips, and thigh supports. So good practice recommends, so that's what's being published, a minimum of 2.5 centimeters of clearance between the hips and the side of the wheelchair, of the chair or the wheelchair. So that's the guideline that was published. So, of course, being a very curious physio, I wanted to know where this comes from. It's basically a panel consensus, but I couldn't find really an actual paper examining, doing research about the tissue effects and the stability effects. So I called, that was on my list of questions to my friend Alexander, and we see what we can do. Because we see in the field that there are so many different setups possible, and on the left you have a little bit of squeeze, and on the right more squeeze. So what is the effect, what can we expect, and how can it influence our clinical decision-making process? Over to you, Alexander.
Yes, thank you, Bart.
First tough question.
Thank you, Bart, for the good start. Welcome also from me, from my side. So Bart came over to me talking about these questions because he knows that I'm an engineer, so I'm talking also a little bit funny because I'm an engineer, and he knows that I'm using finite element. So the first part of my presentation is to give you a little bit a background, what is finite element, and also to explain you why it's maybe helpful to answer the questions Bart raised. Some of the people have been yesterday in a presentation. I I was giving, there was this video. This video is from the company Honda, and it's showing you why using finite element. So this one slide or this first video is a real car crash. The second one you see now is a computational simulation. It looks very close to the real setup because the goal was here to do also some kind of advertisement. But the big difference for the computational simulation is it's in the computer. And what we can see here, we can look inside the car while the car is in a computer crashing to the wall. And the benefit using that method is when we can look inside at every time the crash happens, we can say, okay, which column is the weakest one? Which column fails first? Which is the one I can optimize regarding weight? Which is the one I should be strengthened up to get a better behavior? So finite element is a standard tool in many industries. Car automotive is, I would say, one of the biggest industries using that tool. But it's only one part. And why they are using that? Because they can set up digital prototype. Today, there's no car going to a crash car which was not validated before in the computer. No chance. They will do everything, and when the computer calculations say it's ready, then they will build the car. You have 100% reproducibility. The easiest way when I explain this to people in the seat community is say, let's do a pressure mapping of one before Christmas and the same person on the same cushion after Christmas. What do you think? They will be the same result? Most probably not. It's not only maybe due to the weight change we have over Christmas. It's also maybe, oh, he's relaxing. He was skiing. He has a little different behavior. He has a good day, he has a bad day. So, but in the computer, there is no vacation. We have 100% reproducibility. And therefore, we can, with the internal values, we can do a straightforward optimization. And the goal for them is time and cost for reduction. But the goal why Bart came to me is not this. Bart was interested, can this also provide some information to answer his questions you could not really measure? So the question here is, can we get by this non-measurable quantities a knowledge to answer his question? So the goal is know-how increased by non-measurable values. And the next question is, what if we could do a similar analysis for a wheelchair or cushion? So this was when he came up with that setup. I mentioned the car industry, but Bart, when we finished the presentation, they said, make sure that not only the car industry is using that also the medical society has already started. This is Tina Morrison. Tina Morrison is the chair of the FDA's agency-wide modeling and simulation working group and regulatory advisor of computational modeling for the FDA's Office of Device Evaluation. At the FDA, they have about 200 engineers doing numerical simulation. She is especially working on heart setups. Maybe you heard once about the Living Heart project. This is a heart model in the computer used to optimize that heart setup. And the FDA really supports people using numerical simulations because they say, okay, then we know we have a really 100% reproducible setup. So really also in the medical society, especially regulators say, okay, let's go ahead with that. There is a benefit regarding to that. Finite element analysis enables you the possibility to do mechanical quantities. And I was happy that, what's the name? Gene provided me some foam specimens because Bart said to me, yeah, you will talk about strains and make sure that everyone knows what strains you are talking about.
Does everybody know what strains are?
Could you raise your hand who knows what strains are?
Well.
1, 2, okay, it's good to have the foam blocks. Okay,
there you go.
So you are, in your community, you are evaluating also quantities. You are talking about pressure at the surface. So what is pressure? A pressure strain is if you have a foam block like this, and the strain is then if I compress it like this. Strain is just that the original length or the change is divided by the original length. So it's just the derivation of the displacement. This is the first quantity you are interested in. The second quantity is shear. while pressure is something related to uniaxial, shear is that the two surfaces are moving to each other. So the easiest way is when I would really apply a shear, but these are several blocks, then shear would happen like this, okay? So this is a shear strain. Why shear strain is important? Because there are several publications where it's known that shear strain is maybe more risky to the tissue. The easiest way you can feel that this yourself is if you sit on a flat table, the compressive behavior is not a problem. If you sit on the edge, the one part of the tissue is going down, the other one stays there. And on this edge, a lot of shear, and you directly will feel this, you don't like that. And this is the reason why this is a higher risk for the tissue necrosis. Something which I had to learn when I came to over here, because for me, is you have some different parts. Shear is more in the tissue, but you are using also friction. Friction is in your community, is the behavior when two parts like the human body or the cushion sliding, that there is a friction on the surface. This is the interaction between the setups. And the final one is moisture, which will not be handled, but its microclimate is also very important. The other three ones are mechanical quantities. And based on a publication of Kees Omens from the Netherlands, it's known that the direct deformation results from high but physiological relevant strains, and is a process that these strains leads to the first signs of a cell damage within minutes. So the cell deformation is sometimes or is more significant to the cell damage than, for example, ischemia. And this is the reason maybe let's look on these mechanical quantities using finite element. Just a rough sum up. What I will present you is in the automotive sector already used. They have a different field they are looking for. They're using human body models. I will explain that later, what I'm talking about. For car crash, the left one is developed by Toyota. You see a lot of muscles. It's looking when you're just crashing how the body is moving to make evaluation for the airbag, for example. The other two tools are more for comfort. In the car industry, they are not looking on health, they're looking on comfort aspects. They're looking also on seat pressure distribution, but they normally are not so interested in friction or internal values. So there exist several human body models already, but in this work we will present here, there's a new human body model which I developed. By the way, the right one is from my previous company, so I developed that too. And so far, this one has not a name, so therefore there's a question mark, and I will come back to that later. Because yesterday I mentioned to someone, I have a new human body model. I said, has it a name? Is it Alex? And they said, no. And the last night I was also thinking about Alex, because I will not have only a male model, I have to make also a female model, and I don't want to build Alexa like Amazon, so therefore I will come back to that later. What is the start to do that human body model? What is the input? It's just not, you need some input. The starting point is the geometry. There are two very important geometries in our human body. The first one is the skeleton. Therefore, you can use as an input, you can use CT scan data. For example, we see that here on the left side. And then you need the outer body surface. Unfortunately, I have to mention so far I have only modeled a healthy person. A real patient model is a little bit more difficult as we have not so much data about it. Regarding the body surface, there is an existing scientific work from the Michigan University. They make scans of many hundreds and thousands of people in the US. And at this surface, it's humanshape.org. There you can just download that tool. You just define what's body height, what is body weight, seating height compared to standing height, and then maybe the age. And then out of that, you will see it should start. Then you can just play around with the sliders, and out of that, based on their data, you can generate the outer surface. And they have also made it available that this surface can be downloaded and further processed in the next setup. So we have geometry of the bones and the outer surface. In between, we have the tissue. So what we are doing then with that geometry. And there now the wording finite element comes into play. So we have that geometry, and out of that geometry, we generate a mesh. So you can see that. I have here the geometry of a standing person, and this is just in small elements. It's distributed by small elements, which defining that setup. And finite element enables you that at each position you see where two elements have a node together, you can compute the mechanical quantities we talked about. You can compute the strains, you can pressure, shear, whatever. The question when I have done, there was a question when I have done the last presentation 2 years ago in Nashville. People are not sure what this is. It's not a comic, but I thought when I prepared for this presentation, something which could help them is this picture. I think most of you know that picture. It's about the matrix film. And maybe you know that the matrix itself, it's not real. It seems for everything for them it's like real, but it's not real. It's just there is the scene when they finally have these three agents there that Neo sees really the numbers, that this is not real. It's just a matrix, a system of numbers computing together and showing then the behavior of that setup. And this is finite element. You have the geometry, and the geometry is converted to this part of the matrix. And this enables then you the computation of the requested mechanical quantities. So this is now the human body without a name. And what are the main parts? I converted the geometry, the skeleton, pelvis is important, lumbar spine is important. We have the corpus. We have here also the lumbar spine. We have intervertebral discs. Some muscles are required to have postural stability. So here on the right side, you see the detailed model, nucleus, annulus for the lumbar spine part. So these are the main parts, and together with the tissues. So this is the geometry, but the matrix needs also how it reacts. Is not only geometry, it's also material properties. The properties are taken from literature values. There exist a lot of values based mainly on animal tests. What we see here is Van Locke. He tested here, this is a fresh slaughtered pig muscle setup. He also investigated not only one muscle tissue, he investigated also how muscle tissue behaves when you apply a load vertical to the muscle fibers, in fibers direction, or a shear to that. So you see, you have not only to account for the different tissues like fat tissue, muscle tissue, skin tissue, also the tissue itself has to be taken into account. And this is then another input, which is then the combination, the filling part with the geometry to build up the matrix. You have the geometry and then how the matrix should behave when a displacement or a load is applied. Obviously, animal test, animal tissue is not enough. So you have also to validate this setup by additional quantities like putting the mannequin on a pressure map to see that it's really correlating with the real setup. The other part to do the analysis of the question of Bart is that we have also to work on a wheelchair. I settled up for this a standard wheelchair design which is based on technical drawings of an existing brand. So you see it looks really, I would say, realistic. And so beside the frame and the wheels, you have also to model the cushion itself. In this setup, I modeled a cushion of about 50 mm thickness. And also for that, you need some input. What means you just take a foam block. In the US, we take ILD. In Germany, we take KPA. And you do test on this foam block and see how this foam behaves under this uniaxial test. So this is the input. And then you have to convert it also to a part of the matrix. What I think it's important regarding foam, and I think this is also something important regarding the evaluation, is foam is like a house of cards. The walls are made of polymeric setup, rubber. And what you see here, this is the result of this test. So this shows first we have a force increase, then we have almost no crease, although we have more deformation, and then finally we have a crease. The walls of the house of cards take here the loads. The loads cannot take more load, they buckle. Then we have a lot of air in the foam, which is moving out. Therefore, we have no further increase of the forces. And finally, we have bottom up. We say densification. Finally, there's only rubber, and then we see a strong increase. Why I want to mention that is when you do work on a foam cushion, and someone is sitting it, and you reach already that state, the bottom out, then the softness of the foam is gone away. This is another mechanical quantity you can compute to evaluate an existing design. Now we put both together. This means just in this matrix, I have the wheelchair there, and the human body model is there. I put it on top. Just at the beginning, it's hovering. Then I define contact, what means I apply a load to the human body model, which is gravity. When it will sink down, it cannot penetrate the wheelchair. There's a contact formulation. And it's also, this contact formulation has also a friction that it not just slightly slides. Obviously, friction coefficient can be varied based on the top material. If you have a gliding surface, for example, you can reduce that and you will see the effect on that. I hope it will work when I have, yeah. I just want to show you something. So in this animation, you will see now, this is the starting point. Okay, you see now the mannequin is settling down. Interesting. But the most interesting part is what I can do, I can make a cross-section wherever I want. You see now the tissue inside. And what I can also do, I can scroll wherever I want. And this is the benefit. At each moment when the mannequin is settling down, now we see only just the picture. I can see how big is the movement, how big are the strains, how big are the stresses, and based on that, I have more measurable quantities to evaluate a design, which could help maybe Bart to give an answer to his question. So what are the typical results related to what we have, these mechanical quantities? So we have pressure. So we see now the body surface is transparent. It settles down as before, and we can see how the pressure, the normal pressure, behaves. Just for your information, Bart mentioned to me, this is Newton square millimeters. Red is about 100 millimeters of mercury. So just to see where we are and which range we are here. Another value which is not so easy to evaluate for you in real world is friction. What you see here is the forces acting between the body surface and the cushion surface. And you see there's red and blue because when the IT is going down, on the one side I have friction in this side and on the other side in this side. So both directions, and therefore I have a plus and a minus into that. So just for clarification, because later on we will see more about this. So these are the two values on the body surface. Next one is pressure, but not on the body surface. It's just in the human body. Once again, and this is just to prove that I have not told you something wrong, we see the same process settling down, and we see, just a second please, we see how the pressure develops in the human body. And when I come back to the question of Bart, when there we have almost no gap between the side guards and the human body, it's not enough to look in the outside. It's also very important to look in the inside. And when we just check here, so here, this is the area of IT, and you see at the beginning we have almost no strain, and then finally it shows up that there is a lot of strain. Because the whole load is coming through the skeleton to the pelvis. And the pelvis is a bony prominence. It's somewhere here. When we have the body surface here and measure there, so here we apply the discrete force. And typically, the force is transmitted to a surface area. So what we measure here as a pressure is much lower than the bony prominence. And therefore, it's important to look inside the human body to see what's going on and to compare, okay, is this really the value we are looking for? And the same is possible for shear. I will not, because it takes always a while. Here now we see the shear forces which are in front of the IT. While we seated out, he wants to slide forward. And foam doesn't allow him to slide forward. And therefore, we have some shear inside the human body in front of IT. But the question is now we have this colorful tool. And if we look only there on the maximum values, is this helpful? No, it's not. And therefore, we have been working together and thinking about how can we analyze the data. What you see here is now the same animation, but from the human body, we see only now a specific, the volume which overcomes a specific threshold. You see at the beginning, there is no tissue. And then the value is evaluated for shear above 50% of shear strain, which is based on some publications of Kees Omens, a higher risk for pressure cells. And what we see here on the left side, and I repeat the detail on the right side, at the beginning, obviously no load, but when the pelvis is settling down, we see, okay, more and more tissue is just over exceeding that threshold. And this is a possibility that we cannot say, we can compare how much volume. But still the problem, if I have these maybe two different cushions, it's still a problem. This is a colorful picture, but I need numbers. So what we introduced on top of that is that we just say, okay, we can calculate the volume at every stage of settling down, which exceeding that. And we convert that not to this colorful picture, we convert that just to this VSD mapping. It's just a bar plot. And this bar plot is showing you, it's evaluated for the tissue around the IT, how much of the tissue you see, it's centimeters cubic, how much of the tissue is between a positive setup and minus 10% of shear, how much is below minus 10, below minus 20, below minus 30, below minus 40, below minus 50. And now using that bar plot and have another cushion and do the same, I directly can see what is the difference and which one has a higher risk. And this is a possibility by a simple bar plot to convert these very critical values to a readable evaluation method. It's up to you.
Right.
It's too long.
All right, so that was the first question. The second question I had was non-clinical. It was about what's the meaning of life, but that was a bit too complex to compute. But the next question I had for Alexander was the squeeze effect. What is now the width and the squeeze effect specific to postural stability and tissue deformation? I wanted to know that because we know that it may cause tissue defects, but what is the benefit in terms of posture? And I hope we can get some data on that now.
I hope to. So he came over and said, okay, this is the question. And then I will write this combination of the mannequin with the wheelchair. On the guideline, they have specified 2.0 centimeters or 2.5.
Which is about 1 inch, yeah?
Yes.
Because they do inches in the States.
2.54, yeah. I know that. So, and then I said, okay, let's move the side guards to the different scenarios which could be interesting. So on the left side, we have almost 1 inch. On the middle part, we have almost half of an inch. And then finally, we said, okay, let's do the same analysis, but have no gap. Because we heard some people prefer to have a squeeze because say, oh, the tissue, the fat tissue allows that. It can be squeezed. And we want to use that variation to see the influence of that. On this slide, you see now for each of that, looking, here we have a transparent human body, and I only show the pressure on the side guards due to the contact with the human body. Sorry. Left is 20 mm gap, and you will see nothing. when the human body settles down, which I modeled, the expansion was about 1 centimeter on each side. If I have a gap of 2 centimeters, no contact could occur to the side guards. When I look to the second setup, I hope you can slightly see it. There's a small peak somewhere here. So you see it maybe here. There's a small peak where there happens a contact between the tissue and the side guards, but no continuous contact. And if we have no gap, then we see we have a continuous contact. This is the frontal part of the thighs, and here this is the position of trochanter major, and we see there's also contact. So this is the consequence if I have no gap for this. But this is not enough because this is just looking on the contact values. So we just did the same and look now, okay, how the tissue behaves internally. So this is a cross-section here on trochanter major. On the left side, we see the compressive strains in this direction, so how much the tissue is compressed in the lateral direction due to the contact with the side guards. On the right side, we see the same result with no gaps. And we have to focus here on trochanter major, and you see there, if we have a gap, no strain, no red. If we look on that setup which has no gap, we see here now there is a pressure. There's an internal load onto the tissue. So the squeezing effect has really the risk that their tissue deformation could occur. So it's not just it moves away to something. So this is one of the questions. Okay, squeezing, yes, you can do that, but be aware if there's a contact, you have a loading on the tissue, which could be a risk. On top of that, people are not sitting just upright there. They want to move. Okay? And then we said, okay, they want on the one side this postural stability, but this postural stability also will give you a problem that, so I applied here a movement of the upper body to the lateral side to show the postural stability, that also then the tissue, due to that movement, the loading here is increased. So you have the benefit, more stability, but you have to be sure when you are moving, more higher risk of a pressure ulcer, also in trochanter major in this setup. So what we conclude here regarding the question of Murat is I also evaluated how much force I applied to that the human body is moving, because this is a question, what is the postural stability? And so the blue line is for the setup with a gap, and the red setup is without a gap. And we see there's at the beginning, a directly increase, and always the force is higher for that, because due to the side guards, you need more force to bring the human body to the left side. So this is a quantity for the postural stability. So we can see that there is more postural stability, but nevertheless, this goes along with the risk of pressure sores or pressure ulcers. So you have to make a compromise. On the other side, when we look on the initial setup with a gap of 20 mm, so there we have less stability, but no risk of pressure sores. And based on the study, I would say, okay, 10 mm is a good solution, because we see when we settle down, we have a first contact. We still can allow more movement because we have not too much tissue deformation, and but still we have postural stability. So this is one of the conclusions we found for the first question.
Right. It was very exciting to find it out. Of course, I still have to make proper clinical decision making, but at least I have more information than just following the research guidelines out there. So that was a good one. So I got really excited, and I guess I said, well, it's time for the next question. And I said, well, something that puzzles a lot of people, and that is, what is the knee angle effect on tissue deformation? We know that people who sit for long times have short hamstrings, and if you sit with short hamstrings, the effect of your knee angle must have an effect on pelvis, and it must also perhaps have an effect on what happens inside of the tissue at or around the ischial tuberosity region. So I got a couple of cases here in the practice, and we have all different footrest positions, and they will be largely determined by the choice or the selection of the type of wheelchair I'm making or the adjustment of the foot supports. So what is the influence there, Alex?
Okay, we use the same setup and settle the human body model down, and the wheelchair is the same as before. And then after settling down, we say, okay, when tibia is moving or fibula is moving, we have a direct connection to our pelvis, which is somehow the shortened hamstrings setup. It's a little bit idealized, but in reality, always there's a possibility of a slight movement. And then we said we apply a slight extension, knee extension, which is shown slightly here. It's not really a lot. And to see what causes this inside the human body. And here we evaluated that based on the two quantities. We have shear and the friction. Here you can see the shear part internally, and you can see before in front of the IT, it's only slightly, but I have more information about that next slide. You see the red is increasing. Obviously the tissue, the pelvis wants to move, the IT wants to move, and then we have an increase of that setup. We see also effect here for the friction, because at the beginning we see there a change of the signs, because you see here now more friction occurs to that setup. So there is a risk that this movement of the lower leg induces also some shear. And just not these colorful pictures. We looked once again on VSD internally, because it's really showing you more. This is the initial state you have seen before, and we see volume exceeding the 50% is increasing. So what means it's not only that we have more shear at maybe a risky level, which is the 50%. By the way, there's ongoing work from Kees Omens to qualify that if this is the value or if there may be other values. And once again, I do the VSD plot. And what you see here is the blue we had before. Then I have the evaluation at 2.5 degrees and at 5 degrees. And you see that especially at 5 degrees, at each level, especially here on this level, we see that we have much more volume exceeding that threshold. And by this you can show, okay, this is a risk that if you do that movement like I have shown here, that you will induce more shear, and this is a higher risk for the pressure ulcers. Conclusion, 5 degrees or small knee angle adjustments have already an influence on the tissue deformation with patients with shortened hamstrings. A problem is, I did that movement in the simulation, I just defined a displacement on the heel. When I define a displacement in the computation, I can also compute at that location how big is the reaction force required to move the matrix about this displacement. So I know when I do this 5 degrees, I know how much force I have to apply on the heel. This is the evaluation. Due to gravity at the beginning, we have 5 newtons, which is 1 lbf, I hope. And then we have an increase for that movement to 30 Newton. To make it much easier for me, this is about the weight of 6 pounds. If you apply a weight load of 6 pounds at the heel, you can cause that. And the problem is for me that if someone is holding that to that long lever, he needs not a lot of force to bring that shear to the tissue. And so then we thought about together what could be problems to solve that. Low friction surface, a cushion which allows sliding so that the shear doesn't happen there, maybe a lift up after the patient is settled down, because then if you lift it up, everything is releasing, shear is disappearing because tissue can move, or a wheelchair allowing knee flexion.
Wow. And that was really interesting to me, because I never thought about considering doing a lift up or a weight shift after foot positioning the client after doing a transfer on the wheelchair. So to me that was a revelation. And also that these small adjustments were already showing so much impact on tissue deformation. Then I got really carried away and I said, well, the eternal question, how much should I tilt? Or how effective is a certain tilt angle on tissue? And we all have different opinions about it. There has been some research, but perhaps we can also see what the internal deformation is when we have different tilt angles. So enlighten us.
So the final question was that, and I just want to make a remark. These are first results. And no, because Bart told me it's really one of the key questions. Don't do something, yeah, okay. So what I just did, same setup, and for us in the numerical world, it's easy. I just rotated the ground plate, fixed the wheel on the ground plate and say, please ground plate rotate, and then we will see what happens to tilt in space. So it's the same tool, same simulation. And I looked also here on the left side. It was already difficult because we had 36 degrees of rotation to get the right view because of so much of rotation. On the left side, we see now this is the change of the pressure source, pressure map, I'm sorry. We see that it's really a big reduction here in the cushion, but we see also that here in the lower back, but also here on the scapula, we see the increase. I think this is nothing new for you. But when we look on the friction, we see especially that the frontal parts of the thigh is changing because first it tries to move forward due to that shape, and then when it's going back, the foam wants to keep the tissue. It will not allow him to move downwards, and therefore we see a change of the sides. You see that before that we had red, and then it's really changing the friction direction. But finally, we worked also once again on the VSD, and now you see the same plot. And there was something interesting, and therefore its first results. We see first there is an increase especially of the volume, exceeding the 50%, but finally it's decreasing. More visual is that when I look on the VSD mapping. So these are the results at initial setup, 9 degrees, 18, 27, 36. And you can see, especially when I look here on the 50%, on the 40, on the 30, on the 20, this is when I have 36 degrees of tilt, it's lower. This one is also, but up to 9, 18, 27, everywhere, these are higher values. So first we have an increase, and then we have a decrease of the shear. And one of the conclusion in remarks is be aware when you do this tilt in space that maybe you will always reduce the pressure at the surface, but maybe when you're around 20 to 30 degrees, you will have therefore an increase for the shear. And it's maybe better to have maybe less tilt or more tilt. This is the conclusion what we got out of that.
Right.
And then we are a little bit late, but still in time, I would say.
We are a bit late, but I thought it was just a shame because I had so many other things listed on my question, like belt angles, asymmetric belt angles, shape of backrest, tilt in space, recline effect, the height of the back support. And I was harassing Alexander frequently. I said, well, don't sleep anymore. We just got to do it. But I guess that will be for a next time. But I thought it was already quite interesting what you have already computed. And I think the results show a lot of food for thought. I think we have more brain, you have more knowledge, and I still think it doesn't replace clinical decision making, but at least we have more knowledge on how behavior might be, and then we still have to see how that fits with our individual case. But it definitely already helps us improving our knowledge, and it's better than often what's out there at this moment on these specific topics. I still think there's a big gap in the research on basic wheelchair setups and things that we do on a daily basis. So I think more work from Alexander, more work in that respect could help us with better decisions. And perhaps it can be one of the instruments, finite element analysis, to bridge the gap a bit more. And I don't know what you think, but I hope you're just as excited as I was about this. And it's a great partnership. And,
Yes, it is.
That's good work, right? All right.
So, thank you.
Thank you. And are there any questions, perhaps, or I don't know how that goes?
No, they need to go to the banquet.
Yeah, we have a moderator.
Math.
Yeah.
In the modeling of the lateral displacement at the pelvis, where you had contact with the side guards of the chair, it appeared that the side guard was modeled to have some deflection.
Yeah, it was not totally fixed. It was not totally fixed.
Perhaps did everybody understand the question, or should you repeat the question?
Math asked that the side guards, he has recognized that they are moving a little bit, and he was asking, okay, if they have stiffness or if they are fixed, and I said, no, they are not fixed. They have a connection to the frame, but they are not totally fixed. Obviously, if I will fix them, what means thicken the side guard plate, or use a different material, the effect we have seen will increase, especially for the setup with a gap of 0 mm. Because if the side guard can move, the tissue can also move.
Yeah. So do you think that's part of the consideration in the necessary gap, how stiff the side guards are?
I think that if the side guards are very stiff, no, not really, because when I compare the stiffness of the side guards, although in this model, to the stiffness of the tissue, to think how much force is applied to the side guards to do 1 mm of movement, and how much force I apply to the tissue, I think that the stiffness is like this. I think it's not really relevant. Any other question? I think there's one in the back. Did you?
The belt angles, yeah. He started, but we didn't finish it. Yeah.
The problem is with the belts is, so based on the guidelines, there's about, Bart said, okay, I would be interested to have 90 degrees of belt, 45 and 70. And the problem is when you looked on the model, due to that sinking down, I have here already a lot of tissue deformation. This is making that a little bit difficult. But yeah, I like challenges, and hopefully when we meet again, I have something to share. So far, no results, I'm sorry.
Any more questions? All right.
So please feel free. You can contact us. You see everything here on the slides.
Yeah, all right. If there are no further questions, I think we're going to close the session. And